Hello everyone, we are Group 1 and our topic is music genre classification. These are our content. We'll start by introduction and then talk about the dataset and data pre-processing. Next, we'll talk about our models. And then finally, we'll show our result and discussion. Introduction. Motivated by our interest in music, we're applying machine learning methods to the music genre classification task. We compare CNN, CRNN, random forest, transformer, and autoencoder plus KNN methods on GTZen dataset and report accuracy. Macro F1 score to understand which model best captures musical features for genre classification. As for our dataset, we use GTZen as our dataset. GTZen is a popular benchmark in music information retrieval, containing 10 genres with about 100 songs per genre, each around 30 seconds long. For example, blues, classical, and country.
Okay, so our data preprocessing, we first convert the audio wave to Mel spectrogram, which is basically 2D image with time axis and frequency axis. So the time axis can preserve the temporal evolution characteristic of the sound, making it suitable for sequence models to capture serial features. Next, frequency model making it suitable for models to capture local textural features. And then data compression and dimensionality reduction. Male spectrogram compared to raw audio, it has been compressed along the frequency axis, which effectively converts thousands of linear frequency points into a smaller number of male frequency bands, which reduces the input dimension for the model.
And now we're going to introduce our models. Our first model is the CNN baseline. This is CNN with 3 convolutional blocks, and the channel width increases from 32 to 64 to 192. In each block, we use convolution plus batch norm plus ReLU as the core feature extraction pipeline. After each block, we apply maxpool2D for downsampling. And to reduce overfitting, we add dropout throughout the network 0.2 after block 1, 0.3 after block 2, 0.3 after block 3, and 0.4 in the classifier head. For the classifier, we first use adaptive average pooling to compress the feature map to a fixed size representation. Then we apply a fully connected layer 192 to 128 with ReLU, followed by the final layer 128 to 10 classes to produce the class logics.
And the next method we use is random forest. It's an ensemble learning method that combines multiple decision trees. And the hyperparameters we use we find it by by grid search. And the in trees, which means the number of trees is 200. And the max feature, which means the max feature we use to find the best split is log2 of the total number of the features. And the features we use is provided by the data, which contain 57 features for each 3-second segments of one song.
Our CNN combines the CNN front-end with the LSTM. We use a similar architecture as our baseline CNN model, then use a projection fully connected layer to compress feature maps to 1 to 8 dimension embeddings per frame. So they can be fed into a LSTM to model long-range patterns. Then finally, a classifier maps the 512 dimension sequence representation to 64 units with ReLU and dropout, then to genre logics.
The next one is transformers. We choose a transformer because music is a long sequential signal, and genre characteristic often depends on global patterns such as rhythm, consistency, repetition, and song structure. Compared to CNNs and RNNs, self-attention allows the model to directly capture long-range temporal dependencies across the entire audio clip, which is crucial for genre recognition. Starting from the top, the male spectrogram its input is first projected to a 64-dimensional embedding and combined with positional encoding to preserve temporal order. We then stack 4 transformers encoder blocks, each using self-attention to model global context across time. After that, self-attention pooling aggregates all time step into a single representation by learning which audio segments are most informative. Finally, a full connected classifier maps this condensed embedding to 10 genre logics.
Moving on to our fifth approach, we try something a little bit different. We use unsupervised learning with an autoencoder combined with k-nearest neighbors algorithm. Unlike the previous method, which we explicitly trained to spot specific genres, here we wanted to see if the model could learn the structure of music on its own first. First is the compression. We feed our audio frames into this autoencoder, and its job is to compress the complex audio data down into a tiny 64-dimensional latent vector. And second is the classification. Once we have these compressed vectors for every song, we map them out in the space. We then use a simple k-nearest neighbors algorithm with k set to 5, and it's purely geometric. So if a new song lands in the middle of a cluster of jazz songs, we classify it as jazz. Even without being told the labels during the encoding phase, the model naturally groups similar sounding songs like the red clusters and blue clusters tightly together. This creates a very clean map for our KNN to make predictions. And these are results after our experimenting. These are some accuracy and macro F1 scores and their the model's parameter counts. And as for these results, we have some questions we want to discuss. The number one question is, why does CNN baseline have lower accuracy and macro F1 score? Plain CNN is good at local time frequency patterns in its spectrograms, but aggressively downsampling can blur temporal structure, for example, rhythm. And this helps, rhythm helps distinguish similar genres, and this blurs that.
So next question is that why CRN improves a lot under similar parameters. So we think the reason is that CNN delivers a high quality robust sequence to the subsequent layer, which is LSTM, so that LSTM can leverage its internal memory to model the long-term temporal dependencies and contextual relationships across the sequence.
So for random forest, it achieves an 88.38% of accuracy, which is not bad, and also prove that traditional machine learning works well on this task. But when we're trying to increase the accuracy through tuning the hyperparameters, we fail to increase it significantly. So maybe we have to find other ways to improve the random forest model.
So the next question is why transformer may not win. Transformer models are designed to model long-range temporal dependencies through self-attention. However, in GTZen dataset, each sample is a 30-second excerpt rather than a full song. These excerpts often emphasize local, temporal, and rhythmic texture instead of high-level musical structure. As a result, the structural cues that transformers are good at exploiting are weak or inconsistent. Combined with the relatively small dataset size and the dominance for local spectral patterns, this limits the advantage of transformer-based attention models over CNN-based approaches.
And our autoencoder plus KNN model achieved the highest overall accuracy of nearly 91%. And we believe that the answer lies in the denoising property that autoencoder has. Because the autoencoder is forced to compress the audio into a tiny latent vector, it cannot afford to memorize background noise or recording static. It naturally strips that information away. So this leaves a very clean geometric representation of the songs. And for distinct genres like classical or metal, this makes the clusters incredibly tight and easy for KNN to classify. Essentially, the model runs up the score on these distinct genres, which drives the total accuracy number very high. But if we look at the macro F1 score, which measures how consistently the model performs across all genres, the autoencoder actually scores a bit lower than our CNN plus LSTM method. This happens because the autoencoder is good at compression stuff, but struggles with fuzzy boundaries. Some clusters might get too close to each other, failing the macro F1 score, as the macro F1 considers all distinct genres. Failing on just one or two genres still punishes this score. So while the autoencoder gets the most songs right, the CNN plus LTM, which is the CRNN method, is still slightly more consistent among the all.
So for conclusion, the first one is what we just talked about. The autoencoder plus KNN achieves the highest accuracy, but not the highest macro F1 score. And the second is CNN plus STM provides the best class balance performance, which means they achieve the highest macro F1 score. And for CNN baselines, it underperforms due to limited temporal modeling and loss of timing information. And for transformer plus attention requires larger datasets to fully exploit long-range dependencies. So this is our final project. Thank you.